Hey y'all, this is your boy Mr. Bergman here, section 5.5, roots and zeros, and we're going to talk about the fundamental theorem of algebra and also some graphs. So here we go. I want to do just a really quick terminology review for all you mathletes out there. So we're going to talk about how functions have zeros, equations have solutions, polynomials have roots, and graphs have x-intercepts. And so you'll be able to see here, in order to compare them, what I'm going to keep the same is the polynomial. We got x squared plus x minus 2, x squared plus x minus 2, x squared plus x minus 2, and x squared plus x minus 2. It's just that here we're going to be in function land, here we're going to be talking about equations. Here we're going to look at it as a polynomial all by itself, and here we're going to look at what happens to the graph. Well, surprise, surprise, because it's the same polynomial, it gets factored the same every time. X minus 1 times x plus 2, x minus 1 times x plus 2, x minus 1 times x plus 2, x minus 1 times x plus 2. And so what we can see, when it's a function, we can see one of the big questions on functions is what inputs will produce a 0 as an output. And so here we can see 1, the value of 1 will produce as an input, will produce as an output 0. Same thing as negative 2. Just from this factor right here, x plus 2, you can see if you put negative 2 in here, it'll produce a 0. So the values of 1 and negative 2 are what we call the zeros of the function. And there's two different zeros. Here, in equation land, we've got the same thing. It's a bit easier to solve in factored form, so we separate the two, and we get, you can solve them and get x equals 1 and x equals negative 2. So those values are what we call the solutions of the equation. And the polynomial over here, the polynomial is just the equation without equals 0, and so we can just say the polynomial has these roots. If you were going to graph it, y equals the polynomial, it's a bit easier to see in factored form. The x-intercepts, if you have an x value of 1, then the y value is 0. If the x value is negative 2, then the y value is 0. And you can actually look on the graph, and that's where it's literally going to cross the x-axis. The graph has x-intercepts. So they're very related ideas, and I just wanted to go over the terminology real quick so we can translate between the two. We're going to actually translate between the function and the graph quite a bit. Let's do a little bit of data collection, shall we? So we're going to look at this really strange function. Actually, I have a graph right here on this Desmos slide, which you'll have access to when we come back to class. So here, I'm just going to take a look at, you see, x minus 1 is the, let's see if I can slide it around. I've already slided A, B, and C so that we have the x-intercepts of 1, 2, and 3, which is what I'm looking for. X-intercept of 1, 2, and 3. But if you need to, you can slide these and other values as well. These sliders right here are going to look at the multiplicities. So you got the multiplicity of 1, 2, and 3 right here. So the multiplicity of the first 0 is 3. The multiplicity of the next 0 is going to be 4, and the multiplicity of the next 0 is going to be 2. This function has 3 different intercepts, and so therefore and 3 different zeros, and each of those zeros has its own multiplicity. So x equals 1 has a multiplicity of 3, x equals 2 has a multiplicity of 4, x equals 3 has a multiplicity of 2. And so what you can see here is one idea that we want to look at is how does the multiplicities influence whether or not it crosses the x-axis, like you can see right here. As you go through the 0, as you go through the x-intercept, will it cross or will it bounce? This one crosses, and then this one bounces, and then this one also bounces. Cross, bounce, bounce. And so I'm going to actually write that in right here as my data. Next, let's change up the multiplicities a little bit. The zeros are going to stay the same, but I'm just changing these exponents. So we're going to go 2, 2, 2. Let's see what happens. 2, 2, and 2. The multiplicity is now all 2, and look, they all bounce. This one bounces off the x-axis, this one bounces off the x-axis, this one bounces off the x-axis, and we can record it in our table as such. Let's look at the next one. I don't see an exponent here, so I think what we're just going to say is that that's an exponent of 1, and exponent of 3. Okay, so multiplicity is 1, 1, 3. The exponents are 1, 1, 3. And so let's see what happens. We're going to cross the x-axis here, cross the x-axis here and cross the x-axis here, as you can see, cross, 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 cross. We've written that down in a table. Great. I wonder, are there any patterns here? The real question is, how does the multiplicity affect whether or not it crosses or bounces? Well, if I just slide this, I go, let's take a look at the first one, just A. We're going to go 1, 2, 3, 4. It goes cross, bounce, cross, bounce. It looks, if you look, you'll actually see that anytime that has an odd multiplicity, like multiplicity of 3 or multiplicity of 1, then it corresponds with an x-intercept that crosses the x-axis. And zeros that have even multiplicities like 2, 4, or even 6, 8, 10, if those are the exponents, then they're going to correspond with x-intercepts that bounce off the x-axis. So I hope you enjoyed that, and I hope you enjoy checking out the slide, the Desmos slide when we get to it in class. I don't think we're going to need that anymore. So let's check this out. Here's the polynomial form, and here's the factored form. And if you can translate between the two. If you have the polynomial form here, then to get to the factored form, you can factor it. And we've got lots of techniques for doing that. And if you have factored form, you can go back to the polynomial form by foiling it. Just multiply it all out. If it's really big and complicated, then you can use the box method. Both of these are going to be really important in identifying what the graph looks like. Sometimes it's, if you have an Inspire calculator or Desmos accessible, then you can graph it. If you have it written in either one of these forms. But sometimes graphing it is tricky, and sometimes if there's a letter involved, that's like in the SATs or something like that, then, or it's just sometimes you don't have the access to the full-on function. In any case, sometimes graphing is difficult, and so what you really need to do is be able to translate between both of these, because the polynomial form is going to, if you want to know what the degree of the function is, then you can actually look here on the polynomial form and see, aha, the highest exponent is 2. You can't find that in the factored form. If you want to know the x-intercepts, the solutions, roots, and zeros, the things that we had up here that we talked about, then it's really difficult to find that in polynomial form. But if you have it in factored form, super easy, much more easy to do that. It's you can see the x-intercepts are going to be 1 and -2, and so are the solutions, roots, and zeros, all that. If you're looking for the y-intercept, kind of difficult to find it in factored form, but in polynomial form, you can see it's -2 because this is the number right here. It's if you plug in 0 for x, this term disappears, and then you get -2. I guess you could do the same thing in factored form, put 0 in here, and find out that -1 times 2 is -2, but that's not always, especially with more complicated equations, it's not always easy to do. The end behavior, can't find it in factored form. You can guess what it would look like in polynomial form, but if you just have polynomial form, you can see, aha, the end behavior is dictated by this term, x squared. The exponent is even, the leading coefficient is positive, so therefore it's up, up. If you want to find the multiplicities of the roots, you can't do that in polynomial form, but if you have a factored form, you can see the root or the 0. Maybe I should multiplicity of the zeros. Sometimes you see it referred to as multiplicity of roots, but I think most often multiplicity of zeros. The same idea, really. You have the 0 of 1 has a multiplicity of 1. There's an exponent right here of 1 that you can't see. The 0 of -2 has an exponent of 1 right here. So if you're looking for the multiplicities for whatever reason, you can't find that in polynomial form, but you can easily read it off the factored form. If you want to find the x-intercepts and whether or not they cross or bounce, then you can see here they both cross because they both have an odd multiplicity. This factor has an odd multiplicity. This factor has an odd multiplicity of 1. So therefore, they're both going to cross. If you don't, you can't find that very easily on polynomial form, but you can see it easily on factored form. The big idea of what I'm trying to say here is that you need to be able to translate between both forms to fully analyze a function and its graph. If you have one, you got to give the other, and so and without both, you can't fully look at all the information that we're going to need. So let's take a look. List each zero. This is what some practice problems could actually look like. Let's zoom in a little bit. List each zero of f of x and its multiplicity. I think the shorthand I'm going to say is that this is a 0 and this is its multiplicity, 9m1. So you can see here from this factor, no need to FOIL, no need to do box method, because zeros, when the function is in factored form, you can just look at the exponents. No need to FOIL it out. Here, this factor, you can see x minus 9. Oh, 9 is the number that would make this 0, and the exponent is 1. So the 0 has a the 0 of 9 has a multiplicity of 1. The 0 of negative 11 has a multiplicity of 1 for the same reason. And 8 is the number here that would make this equal to 0. And you can see the exponent is 3, so the multiplicity is 3. Find a polynomial f of x of degree 5 in factored form that has the following zeros: 0, 2, 8, negative 3, 6. All right, so it's going to be, in each of these cases, it's going to be x minus the 0. X minus if you're given a 0 and you want to find the factor, then you do x minus the 0. Everyone say it with me, because it's going to come up a lot and people are going to forget. X minus the 0. X minus the 0. X minus the 0. So x minus the first 0 is this. X minus the second 0 is this. X minus the next 0 is this. X minus negative 3, you could change it into x plus 3 here, and then x minus 6 is here. No need to FOIL it all out or multiply or do anything like that, because you're allowed to list it in factored form. Whew, good. And so degree 5, if you were to FOIL it all out, you would get the first term would be x times x times x times x times x, and that's 5. So great. It would be x to the 5th. Find all x-intercepts and y-intercepts of the graphs of the function. Okay, so here if we have a function, finding the y-intercept is not too tricky, because you just plug in 0, and in polynomial form, it's just actually just going to be this number right here, minus 16. The y-intercept is negative 16. Great. Finding the x-intercepts in polynomial form is going to be a bit trickier. So actually what you got to do is factor, because what we really want is factored form. So you can see just looking at this, I see 4 terms, and then I think we're going to be able to factor by grouping. The greatest common factor of the first 2 terms is x squared, and the greatest common factor of the second 2 terms is negative 16 or minus 16. And so we're left with a factor that is repeated, x plus 1, x plus 1. Great. You could write it once here, and then the leftovers go in the other one, x squared minus 16. Now we still don't, this is not completely in factored form because this exponent is too high. X squared, we can factor that even further and get x plus 4 and x minus 4, because it's a difference of squares. And then we get x plus 1. So now that it's in factored form, we can see the x-intercepts. It's going to be negative 4, positive 4, and negative 1. Boom, right there. This is a great example of how you can't get all the information from one form. You need both. Given functions in polynomial and factored form match the graph. Okay, so, thank you. Whoever wrote this question, you're giving us both versions. That's so nice of you. Because if you only had one version, I'd have to find the other. Let's see. From the polynomial version, I can see the end behavior is x cubed. It's going to give me down-up end behavior. The exponent is odd, and the leading coefficient is positive. And then the y-intercept is over here, positive 24. That's what information I can get from the polynomial form. The factored form, I can get all the x-intercepts. We're going to have an x-intercept of negative 3 here. Of 2 here, and 4 here. So when I write it all out and I'm listing the multiplicities, I'm looking at all the exponents. Exponent of 1, exponent of 1, exponent of 1. So the x-intercepts are going to be negative 3, and that has a multiplicity of 1. The x-intercept 2 is going to have a multiplicity of 1. And I wonder if you can figure out what the x-intercept here is, and it does have a multiplicity of 1. Because they're all multiplicities of 1, and 1 is odd, then they're all going to cross. So, looking at all this information, you can see here, we are looking for x-intercepts of negative 3, positive 2, and positive 4 right here, and they're all crossing. That's great. We can discard the others because, and then we even see the y-intercept. It's down, up. This one is not down, up. This is up, down. But this is the arrow goes down here, the arrow goes up here. So it's down, up, end behavior, and the y-intercept is 24, which is like right about there, which is great. All right, let's see. Here, it's like we've got this function, and just right off the bat, I think what I'm going to do is I'm going to take it from factored form and turn it into polynomial form. And the way you do that is it's basically you have three things you got to multiply, like x plus 1 times x plus 1 times x minus 1. And I think what I'm going to do is I'm just going to use my formula a squared plus 2ab plus b squared to change it into this. A is equal to x, b is equal to 1. So this is a squared plus 2ab plus b squared right here. And then bring along this for the ride. And then actually I can use, I don't think I have the work here to show you, but I can actually use a 2x3 box to multiply this times this. And you get this right here. And then I'm going to distribute the negative and flip all the signs, and this is what I get. These are the same function essentially, except this is written in factored form and this is polynomial form. And now that I have both forms, I should be able to get all the information I need. The x-intercepts and their multiplicities. Factored form. So this factor means that there's going to be an x-intercept of -1 with a multiplicity of 2. 2 is even, and therefore it bounces. The x-intercept of +1 is here. It has a multiplicity of 1 because there's an unwritten exponent of 1 right here. And you can see because 1 is odd, it's going to cross. The y-intercept is going to be +1 because I can see it right here. You know, plug in 0 for x and you get 0, 0, 0 plus 1. That's going to be the y-intercept of 1. You could technically put it in here also, and that would work as well, but it's a lot easier to do it here. What's the degree? Look over here on the polynomial version, and you can see the highest exponent is 3. The leading coefficient, did I list that anywhere? Leading coefficient? The leading coefficient is going to be -1 because I can see it right here on the polynomial form. Alex might ask, what are the zeros that cross the x-axis? And you know, the x-intercepts that cross the x-axis is going to be right here. I found it already. So we're looking at this 1. The x-intercept is 1 that crosses the x-axis. The way that Alex talks about bouncing is that it is a complicated phrase, that touch but do not cross. So that's just what we're calling bouncing. Here, -1 has an even multiplicity, and we already know that it bounces. So you can type in a number of -1. End behavior, we're looking at this. This has a leading coefficient of -1 and an odd degree, so therefore it's going to have up-down end behavior. Now, you could also do an input-output table, but given all this information about the graph, you can actually construct a you could just hand draw this if you wanted to, up-down end behavior. We got the x-intercepts and the y-intercept. So with all that information, you can pretty much connect the dots and see and sketch out a pretty good representation of the graph. So that's polynomial form, factored form, and what it looks like on graphs. The fundamental theorem of algebra. All right, so let me just say right here that this is kind of a big deal conceptually, because there's also like fundamental theorems of geometry and fundamental theorems of calculus and fundamental theorem of probability. There's each of the major mathematics sections have these fundamental theorems, like the biggest ideas that keep on coming back to, and that are far-reaching and are very useful in proving other things. So the fundamental theorem of algebra is that every polynomial equation with a degree greater than 0, that's like all the polynomials we've seen here, like if it has a degree of 2 or 3 or 5 or whatever, or 1, and has at least one root in a set of complex numbers. It has at least one root in the set of complex numbers. You might be like, all right, yeah, they've got some roots. That's fine. As a corollary, the polynomial of degree n has exactly n roots in a set of complex numbers, including repeated roots. That's the word repeated is actually referencing the multiplicity. That might seem like gibberish at the moment, but stick with me. Here's the short version. The degree equals the sum of the multiplicities. So if you had, for example, here, the degree is going to equal the sum of the multiplicities. So for this one, if you had this multiplicity, the sum of the multiplicities is 3 plus 4 plus 2 is 9. So therefore, 9, if you were going to FOIL this all out, you'd get, as the first term, x to the 9th power. Here, if you have the multiplicity is 1 here, the multiplicity 1 here, add them up, you get 2. The degree is 2. The sum of all the multiplicities is equal to 2. This is a far-reaching idea, and we needed to learn about complex numbers in order to talk about it. Fundamental theorem of algebra. There it is. Also, I just wanted to drop here right now, just randomly, that my favorite place to run is the Philadelphia Museum of Art. If you've ever been there, you know Kelly Drive and MLK Drive. They're just really beautiful places to run. And if you enjoy being outside, why don't you tell me in class where you enjoy running or where you enjoy rowing or whatever it is that you do when you're outside. Take care, y'all, and I'll see you in class.